All right. Uh, Hello, class. Um, hope you're doing well. Hope you hope you are having a nice weekend. Technically, so I forgot that it was Memorial Day today, and I had already planned my lessons, so I'm just gonna go through with it. If you don't want to watch my lesson today, you'd rather watch it tomorrow. Go ahead and watch it tomorrow. That's just fine. Um, there's Ivan. Hey, Ivan. Um, So I apologize. I just completely forgot. A couple of announcements. Friday. So by the end of the day today, there will be a final quiz posted. Okay. That quiz will be due Friday. And that will be the last thing for the class. There will be no homework on Friday, so you don't have to fill out the homework form. Just do the last quiz. And it'll cover astrophysics. And it's going to cover content up to tomorrow's lesson. So tomorrow's lesson will be the last one that you need to know about for the quiz. We will also have a meme review on Friday. Okay? And I'm thinking probably Wednesday will be the last lesson. Okay? So we'll just do a couple more lessons and that's it. So I did want to show you, I have been foraging a little bit more, and I'm working on a kukri. So this is my kukri. So a kukri has the blade bends forward a lot, so you hold it kind of like this, and I don't know, it's for like chopping branches and stuff, kind of like a machete. So I think it's pretty cool looking. So this was a railroad spike, and I obviously need to polish the blade and sharpen it and drill holes for a handle, but I think the shape is quite pleasing. And then I'm also working on a chef's knife, which I think this thing just looks awesome. It does, like, I hammered the tip of the chef's knife into that shape. Like, that's 100% hammering, and that was not easy to do. It took me like 2 hours because, when you have a thin piece of steel, and you're hammering like this, it wants to fold over. So you have to go very slow to keep it from folding over and mushrooming kind of when you hammer it. So this is almost perfect. I need to hammer right here, and when I hammer right here, it's going to make this part thinner, but it'll push it out a little bit more because so I actually want the chef's knife to maybe end like right here, because if you're thinking about when you're chopping, if you're chopping something, then you want lots of space between here and your fingers, otherwise your fingers are going to hit the cutting board, right? So, but this is pretty close. Like that's pleasing. I'm happy with this. All right, so let's get to the physics. Thank you. Thanks, Will and Ethan. Okay, getting to the physics. I talked to you about the life cycle of stars last time I talked to you guys, and I wanted to talk a little bit about black holes today, and because people are excited by black holes. But the first thing I wanted to talk about is something that at first appears That's a good idea, Will. I actually have photos of the progression, but I just didn't have it posted them. All right, so uh, first thing I want to talk about is something that at first sight appears unrelated to black holes. Okay, and so what I want to talk about is the energy of an object that is orbiting or that is in orbit. It has kinetic energy, 1 half mv squared, and then it has gravitational potential energy. Okay, and the formula for gravitational potential energy is this one with the minus sign, and it is the one that I taught you right before the AP exam, and I said this is the one that's used in astrophysics. Okay, this is the one that's used in in astronomy and celestial mechanics and so on. When you have things that are not close to the surface of the Earth, this is the formula for energy that you use for gravitational potential energy. Okay? So what if we had something like Earth, and Earth has a radius, big R. By the way, little m is the mass of the thing that's orbiting, and big M is the mass of the central body. Okay? So what if we have a rocket? Okay, so here's the rocket, and the rocket starts out with some initial velocity, and it has that velocity, and it just starts heading away from the Earth. Okay. And once the rocket achieves this speed, it's just going to coast. So it just coasts away. Now, if we have the old formula for gravitational potential energy, whatever comes up will eventually come back down. But actually, what happens is the higher this rocket goes, the weaker gravity gets. So it's actually possible for the rocket to escape and get away to infinity and never come back. All right? So we would like, and that's called the escape speed. So we would like, what I want to do is I want to calculate the escape speed. And so what that means is this is the speed that if you threw something straight up into the air with the escape speed, it would go up and it would never come back down. Okay? It would leave and it would never come back. This is the speed that rockets need to achieve in order to leave the Earth. Okay? If you want to leave the Earth and go to Saturn, for example, you have to achieve the escape speed from Earth. Okay? So, to calculate the escape speed, we are going to use conservation of energy. So the energy basically at launch has to equal the energy when it escapes. So the energy at infinity, the energy when it gets really far away. Okay? So at launch, the speed is 1 half mv squared, and the kinetic energy is 1 half mv squared, and the gravitational potential energy is negative g little m big M over r, where r is the radius that the rocket is leaving from. So if it's leaving from the surface of the Earth, then this would be the radius of the Earth. If it's leaving from orbit, the r value would be larger than the radius of the Earth. Okay. All right. Now, what is the energy when it gets to infinity? Let's assume that it barely has enough energy to make it to infinity. Okay? If it barely has enough energy to make it to infinity, then when it gets way the heck out there, its speed is going to be essentially zero. So the kinetic energy is zero. And because it makes it so far away, the denominator, the r value that it makes it out to, it makes it out infinitely far away, so the R value is infinity. Okay, so the kinetic energy is 0, and the potential energy is also 0, because we're dividing by infinity, so we're dividing by a big number. So that means that the energy out in infinity is equal to 0. Okay, so we have this equation right here, and we can take this equation and we can solve for the escape velocity. And if you do that, you get that the escape velocity is square root of 2gm over r, where m is the mass of the central body. Okay? So in particular, it says that the more massive the planet is, the greater the velocity has to be in order to escape. Okay? Excuse me. So, if you calculate it for Earth, the escape velocity for Earth, if you want to leave the surface of the Earth, you can calculate this using the mass of the Earth and the radius of the Earth, and what you get is 11 kilometers per second. So if you were able to throw a rock upward at 11 kilometers per second, it would go up and it would never come back down again. All right? This is neglecting air resistance, of course. Another interesting thing about this equation is that it works in reverse, right? If you have an asteroid or a rock that is floating out infinitely far away and it falls and it hits the Earth, it's going to hit the Earth with the escape speed. So, for example, the asteroid that destroyed or that killed off the dinosaurs hit the Earth with a speed of around 11 kilometers per second. Okay, so it goes both ways. It's if you want something to leave and never come back, what speed does it have to have? Or if something is falling in from a great distance, what speed will it have when it hits? So one of the things so where does this lead to black holes? Okay, so you could say, what if the escape velocity or the escape speed was equal to the speed of light? The speed of light is denoted by c, and its value is 3 times 10 to the 8th meters per second. So what if the escape speed was the speed of light, or greater? Then that would mean simply that nothing could escape, because nothing can go faster than the speed of light. Okay? So a black hole is an object where the escape speed is greater than the speed of light. Okay? So we can actually take this equation and turn it around, and we can say, well, the escape speed is square root of 2gm over r. So we could say, what if that is the speed of light? And we can solve for r. What we get is that r equals 2gm over c squared. This would be the radius of the black hole. Okay? Which is called the Schwarzschild radius. So, interesting story. Einstein created his theory of general relativity, and he thought it was so complicated that a solution would never be found. And then this guy, Karl Schwarzschild, actually found the first solution, and it was a black hole. So the very first solution that was found to Einstein's theory of relativity was for a black hole. And interestingly, the guy, Carl Schwarzschild, who found it, was fighting in World War I, and he was actually in the trenches. So he was, working out the mathematics of general relativity in the trenches. Pretty fascinating. So this is the mass of the black hole. This is the radius of the black hole. So what would its size be? So let's go ahead and calculate what is the Schwarzschild radius for the Earth. So the interpretation of that is if you were to take an Earth mass object and turn it into a black hole, compress it into a black hole, how big would that black hole be? All right. So let's calculate it. You have 2, g is 6.7 times 10 to the minus 11. Mass of the Earth is 6 times 10 to the 24th over the speed of light squared. Let me crunch the numbers. And we get about 0.9 centimeters. So the Earth would make a very, very tiny black hole. You could hold it in your hand. All right. I mean, you couldn't hold, if you touched it, then your entire body would get sucked in. But it would be something roughly the size of a marble. Pretty interesting. So, anyways, let's talk about sort of the anatomy of a black hole. By the way, what this says is that the more massive the black hole is, the bigger it is. So in particular, as a black hole eats gas and dust from outer space, it gets bigger. Okay. So if we look at a black hole, it has a certain radius. Now, this is the Schwarzschild radius. Now, is the black hole actually, is this a hard surface? And the answer is no. This is basically the point of no return. If you get within one Schwarzschild radius of the black hole, then even if you tried to get out at the speed of light, you couldn't. So once you cross within one Schwarzschild radius of the center, you're never coming back. Okay? In particular, light can't escape. So this is the basically this. If you were to look at a black hole, you would see darkness out to a Schwarzschild radius. Okay? It's the point of no return. And the boundary is called the event horizon. So if you cross the event horizon of a black hole, you will never come out. Okay? So we don't know what is happening within the event horizon of a black hole because by its very definition, once you cross the event horizon, no information can get back out. Okay? So the data from inside the event horizon is impossible to send out to the external universe. So you could have the answer if you cross the event horizon. You could solve the question of what happens within a black hole, but you wouldn't be able to share that information with anybody. As far as we know, the actual mass of the black hole, because nothing can stop the gravity at that point, we actually think that all the mass is concentrated at the very center. Okay? And this is called the singularity. So A black hole has an event horizon and it has a singularity. So it's a very simple structure as far as we know. If the black hole happens to be spinning, which most black holes are, there's also a region, it's kind of an oval-shaped region about the black hole that is called the ergosphere. And the ergosphere is kind of interesting because it is the radius, it is the distance at which once you cross the ergosphere, you have to rotate with the black hole. So the black hole is actually dragging space-time around it in this kind of whirlpool. And once you get within the ergosphere, even if you were to travel the speed of light, you always rotate with the black hole no matter what. Okay? So it's basically the world. You could still leave, but you couldn't go against the swirling of space-time. Okay? So that's kind of interesting. And then outside of that, we're looking at the black hole from edge on. There's a giant disk, sort of like the rings of Saturn around the black hole, only much bigger. And this is called the accretion disk. So the accretion disk, accretion means to collect. If you accrete, it means to collect. So the accretion disk is the stuff that's on its way to being eaten by the black hole. Okay? And it's actually the only way that the black hole can eat is if the stuff in the accretion disk loses energy. Because if the stuff is in its orbit, then the orbit is stable, right? So what actually happens in the accretion disk is the particles that are orbiting the black hole, they bump into each other, and maybe one of the particles gets bumped in a way such that it slows down. And when it slows down, it's able to fall into the black hole, okay? So the stuff in the accretion disk is bumping into each other, and it's that bumping that causes the mass to fall into the black hole. Also, because of the bumping, the accretion disk is very hot because the bumping it causes friction. Okay, so actually we can see the accretion disk around black holes. Okay. Now, some of the matter that falls into the black hole actually gets ejected along the spin axis. So what we find is that black holes often have jets. These are called jets. And the physics of the jets are not completely understood. But somehow, some percentage of the matter that would be falling into the black hole actually gets shot out along the poles of the black hole. So those are called jets. I have seen Interstellar. And so we know that jets have to do with magnetic fields around the black hole. So magnetism somehow deflects the particles along the axis. But we can also often see jets emerging from the black hole. So you can't see the black hole itself, but you can see the stuff around it, and you can infer that there's a black hole there. In fact, I'll talk about that in a different lecture. One other thing I wanted to talk about just really briefly is black holes actually have what's called Hawking radiation. Okay. And Hawking radiation is actually electromagnetic waves emitted by the black hole. So it's possible for the black hole to emit electromagnetic waves from just above the event horizon. That's called Hawking radiation. It was discovered by Stephen Hawking. And Hawking radiation, according to E equals mc squared, um, if the black hole radiates away energy, then it also radiates away mass. So if a black hole doesn't eat, it actually gradually gets smaller. Okay. But the thing is, it turns out that the amount of Hawking radiation actually goes down with the size of the black hole. So big black holes are actually more stable than little black holes. One thing we're actually anyways, this effect of black holes getting smaller if they don't eat, it's called evaporation. Okay, black hole evaporation, and we actually think that it should be possible to, in particle accelerators, to smash together particles and make miniature black holes, which then evaporate and produce a burst of radiation that we can then see. So we actually think that at some point in the future, we'll be able to create mini black holes that are so unstable that they evaporate immediately, and we can view the evaporation of the black holes. So you might think this is incredibly dangerous. Are we going to create a black hole and destroy the entire planet? But the answer is no, it will be safe because the black holes that we make will be so tiny that they evaporate almost instantly. So it'll be pretty cool. I think at some point in our lifetime, we will experiment with black holes.